In this section, we're going to perform an overview of bonding and specifically look at the properties of solid compounds. There are four types of solid compounds that we're going to look at in this lesson. And the first type of solid compound that we're going to look at is demonstrated over here. And this is called a network covalent solid. So a network covalent solid is when the particles inside the solid, so the atoms inside the solid, are all bonded together in this crystalline network with covalent bonds. So this atom is covalently bonded to that atom, which is covalently bonded to that atom, so on and so forth. So the atoms are all connected through covalent bonds, and it's a network. And when there's so many of them together, this creates a large solid. So examples of this would be silicon dioxide, which is demonstrated up here. This is an example of a silicon dioxide crystal. Silicon carbide, which is called carborundum. And also just carbon in both its diamond and its graphite form. This structure that you see here, this is graphite. So this is carbon in its graphite form. And we can see that the carbon atoms are bonded in these 6 carbon rings, which are then bonded to each other, again in a network. But they make these flat networks, or these flat planes, or these flat sheets of carbon networks, and that's graphite. So the force of attraction, the bonding that holds all these atoms together in this crystalline structure is, as we said, it is a network of covalent bonds, which are extremely strong. And so atoms are all bonded together right? As you see, the atoms are all bonded together through covalent bonds to form one large, what is called a macromolecule. So macro meaning large scale, macromolecule. So when the atoms are all bonded together and there's no end to their bonding, they just keep going in this one large crystal, then technically that one big large crystal is just a molecule, because all the atoms within that crystal, they're all bonded together with covalent bonds. So that's what we call a large macromolecule. And so macromolecule just means a giant molecule. The factors that increase the strength of the bonds, well, this depends on the shape and geometry of the covalent network. So for example, if we look at silicon dioxide, it has a distinct shape to it that gives it a lot of stability and structure. The same thing with diamond. Diamonds are notably extremely hard, right? And it has to do with the way that the carbon atoms are all bonded together in the crystalline structure. Graphite, on the other hand, has these rings, as I mentioned, that occur in sheets. And the sheets are, as you can see, they're slightly separated, which means that these sheets can actually move past each other and glide past each other. The sheets themselves, however, are quite tough and extremely hard to break. So an example would be looking at diamond structure, which is extremely hard, and there is no shifting or gliding in a diamond, versus graphite. So both the same substance, right? Both just carbon, but have a different geometry of the network covalent bonds. If we look at the specific properties of the network covalent structure, the melting point of the network covalent structure is going to be extremely high. And the reason why it is extremely high is because all these bonds are covalent bonds, and those are the strongest bonds, or some of the strongest bonds in chemical bonding, right? So in order to break those bonds, you need quite a lot of heat, and even then it will likely involve a chemical reaction. So you don't get a change of state typically before you end up with a chemical reaction, because you're actually breaking covalent bonds. The hardness is very hard. Okay. And it is brittle under extreme pressure. So brittle under extreme pressure. The next question is solubility. Like, will these particles break off if you try to dissolve them? Well, if you're thinking accordingly, these particles are bonded together with covalent bonds, which are extremely strong. So no, these particles will not break off very easily. So the solubility is none, or no solubility. Okay, you put graphite or you put diamond in water and it certainly will not dissolve. Conductivity of a solid. Remember that for conductivity, you need to have moving charged particles. That is the basic requirement for conductivity. In none of these cases, in graphite, in silicon and in diamonds, do you have any sort of conductivity. So you have poor conductivity. What I meant to say, however, was graphite is actually the exemption, because these 6 carbon rings actually produce what's called delocalization of the electrons. So it actually provides a pathway for electrons to travel. So the electrons all get shared between all these carbons, and they can travel along these rings. So the electrons are delocalized, right? And cause, and if they are delocalized and they're moving and they're traveling, we have now moving charged particles. So graphite is the exemption, is the exception, since it has delocalized electrons. And that word delocalized means unlocalized, and that's because the electrons are no longer local to just one carbon atom or in the bonds between the carbon atoms, but they're actually traveling along these ring structures. Again, conductivity of the liquid or aqueous solution, well, since it's not dissolving, there can be no conductivity. And response to mechanical stress is that it will shatter under extreme pressure, as we indicated. Shatters under extreme pressure. So this sufficiently covers the first type of solid that we were looking at today, which is the network covalent solid. This next solid that we're looking at is a solid that you have already seen, and this is an ionic solid. So this is like an ionic crystal, a salt. Okay. And so examples of these would be like, for example, sodium chloride is a classic example of a salt, and this is, a sodium chloride crystal lattice, or, sodium thiosulfate, or copper 2 chloride. These are all examples. And if we go up to the top, well, what are the forces of attraction holding this solid together? Well, we have ionic bonding holding the solid together. So, in the way that there was covalent bonding holding these atoms together in this covalent structure, in this case we have ionic bonding holding the ions together in a crystal lattice. And so to go just a little bit deeper, what is ionic bonding? Well, ionic bonding is the electrostatic attraction between oppositely charged ions within the crystal lattice. So what this means, electrostatic attraction, that means opposite charges attract. The opposite charges are attracted, and that creates a regular pattern, which is the definition of a lattice, a regular pattern of positives and negatives in a crystal format. So if we look at what are the factors that increase the strength of ionic bonds, so what factors would make some ionic crystals stronger than others? Well, the first factor is smaller ions. So the smaller the ion results in closer packing within the crystal. So if you have closer packing within the crystal, that will create a denser crystal, and that will make it stronger. So for example, if you take a look at sodium chloride, the sodium chloride crystal is stronger than the potassium chloride crystal, which is stronger than the rubidium chloride crystal. Okay? And we look at the strengths by looking at their melting points. So if you look at the melting point for sodium chloride, and you look at the melting point for potassium chloride and rubidium chloride, sodium chloride would have the highest melting point of those crystals. The other factor that leads to a difference in strength is bigger charges, so larger charges on the ions. So if you have larger charges on the ions, then you will have greater forces of attraction. So an example of this would be aluminum fluoride with a 3 positive aluminum has a higher melting point than magnesium fluoride, which has a lower melting point, that's a 2 positive charge, and then which is even higher than sodium fluoride, which is just a 1 positive bonded to a 1 negative. Okay, so the higher charge has the higher melting point. So if we look in general, what are the melting points of ionic solids? Well, the melting points tend to be pretty high. The hardness is hard, but it is, however, brittle, which means it will shatter. Okay. The solubility is most dissolve in water. However, there are some exceptions, and you will remember your solubility chart from last year. Remember, we looked at certain ionic compounds that had low solubility, and so when we saw a compound had low solubility, we had to write it as a solid, or that's the ionic compound that formed the precipitate. So most ionic compounds that are pretty soluble in water, except for those with low solubility, so most dissolve in water. conductivity of the solid. Again, moving charged particles. Does this have moving charged particles? No, because the charged particles are stuck in the crystal lattice. So there is poor conductivity as a solid. Conductivity as a liquid and aqueous solution is high because if you get this to the molten state, then you just have pure sodium ions and pure chloride ions floating around in a liquid, so you have moving charged particles. Or if you dissolve it, then you have sodium ions surrounded by a water shell and chloride ions surrounded by a water shell, but they're moving throughout the solution, so you have moving charged particles, and this creates high conductivity. Response to mechanical stress, as we said right here in the hardness and texture, it will cleave, which means to split in two, or crack as like charges align under pressure. So you recall from last year we talked about this. When you apply pressure on a crystal lattice, you shift the ions down so that they align with their like charges, which causes repulsions, and that means the crystal cracks apart. The third solid that we're going to look at is the metallic solid. Again, this is a topic that you studied last year. And so we'll just put right here, metallic solid. And examples of that are types of metals, right? So metals, but also alloys as well. And alloys are just mixtures of metals, such as, like, for example, brass, right? So metals could be like iron or platinum, but like we said as well, it could be an alloy like brass. So here, right, is the model that I have used as my diagram for this example. And this is called metallic bonding. And you will recall that metallic bonding is the sea of electron model, which is that the metals release their valence electrons to a shared common pool of electrons, which we would now say are delocalized, right? Because these electrons are not local to the metals anymore. They're released into the sea, and then the electrons can navigate, if you will, throughout the cations in the solid. So the forces that will increase the strength, or the factors that will increase the strength of the bonds, is if you have smaller metal ions. Okay. So if you have smaller metal ions, that will increase the packing of the cations in the sea of electron model, which will increase the strength, right? If you can pack more of the metal ions together, it's going to make the metal stronger. So if you were to take a look at your melting points again, so we look at melting points as an indication of strength. Scandium has a larger melting point than calcium, which has a larger melting point than potassium, right? Scandium being the smaller of these three metals. Okay. The other thing that will affect it is more valence electrons. Right? Because if it has more valence electrons, that means it has more electrons released to the pool of electrons, and if you have more electrons released to the pool of the electrons, you have stronger forces, right? So you have a stronger force between the pool and the cations. Just get rid of this. And cations. So if you looked at, for example, vanadium has a 5 positive charge, and so vanadium metal tends to have a high melting point because it has released 5 electrons to a to the shared common pool, creating a very strong, and it's sometimes referred to as quote-unquote electron glue, because the electrons flowing in between it are like the glue between the cations. So the melting points are mostly high. The hardness and texture is, we would say, ductile. So you can tend to stretch it out and make wires out of it, or malleable, which means you can hammer it into sheets. It does not dissolve in water. Conductivity as a solid, well, we have moving charged particles here. You have moving electrons, so the conductivity of the solid is good or high. Conductivity of a liquid and an aqueous solution is not applicable, right? So like, for example, molten metals, I would say molten metals have good conductivity, but aqueous solutions is not applicable because they don't dissolve in water. And response to mechanical stress is that it can change shape, can bend, or it can flatten or be pulled. All right, so that covers metallic bonding. Okay, so the last is molecular solids. And so molecular solids are basically any solid that is made up of a molecule, right? So for example, this, I believe, is sucrose, which is sugar, right? Sugar crystals, or solid sulfur, okay? Or even like, solid water, which is ice, is a molecular solid, okay? And so, one more thing, plastics. Plastic is a type of a molecular solid because it is made up of these very long molecules called polymers. So if we looked at the force of attraction between these particles, the force of attraction between molecules, we have a name for it. It is intermolecular bonding. Okay, so examples of that are like London dispersion forces, dipole forces, and hydrogen bonding. The forces, or rather the factors that increase the strength of that, well, for London dispersion, we know that it is the number of electrons. So the higher number of electrons, the stronger the forces of attraction. We know that if you have a strong molecular dipole, so if you have a very strong delta positive, delta negative, that could increase the strength of the forces between the molecules. And then finally, if you have the number of hydrogen bonds. So, molecules could have a number of sites where hydrogen bonding can take place between molecules. So you take a look at the OH bonds, the NH bonds, and the FH bonds within the molecule, and typically that will lead to greater strength. So the melting point of this solid can actually vary quite a bit from low to high. Right? It really all depends on the type of intermolecular bonding going on in that solid. If you have weak intermolecular bonding, then the melting point of the solid is going to be pretty low. But if you have, many hydrogen bonds in a very large molecule that has lots of electrons, well, then the melting point is going to be quite high. And we know, like, for example, plastics are huge molecules because they're made up of these large molecules called polymers. And these polymers have so many electrons in them that it creates a very, very strong solid. So the hardness, though, it depends, right? It can become soft, right? Or crumbly. But again, it also really depends on the types of intermolecular forces that are present. And the solubility is good depending on the solvent. So if you have, for example, a nonpolar substance, well, it's going to have low solubility in water because water is polar. But if you have a nonpolar substance and you have a nonpolar solvent, well, then it will dissolve quite well. Again, conductivity is going to be poor here because it requires moving charged particles and molecules. Even though they might have slightly charged end, the molecules themselves are not charged. And conductivity as a liquid and aqueous solution, poor. Mechanical stress, so some shatter, right, if they're crystalline like sugar, right? Ice shatters as well because it forms a crystal. But in general, there's a tendency to crumble, so to just break apart. So in summary, we've looked at 4 types of solids. We've looked at network covalent solids, which are our strongest of solids because all the particles within the solid are bonded by covalent chemical bonds. Ionic solids, which are quite strong as well, but those are bonded with electrostatic forces of attraction with ionic bonds. Metallic solids and molecular solids. We've also looked at the factors that play an effect on how strong these bonds are, and just looked at specific properties of each of these solids. Okay, thanks for watching.